Welcome back to the course on econometric modeling. This is module 33. Module 33 is part of models with binary dependent and independent variables. In the last modules I had discussed till probit and logit models, and this is the last component or module under a binary dependent variable. So, the last two types of models that we are going to discuss are Tobit and multinomial logit models. So, first of all, talking about Tobit models, this is another important kind of limited dependent variable model. This basically deals with situations when there is a corner solution response. So, such a variable is 0 for a non-trivial fraction of the population, but is roughly continuously distributed over positive values. So, this implies that the variable has observations where a significant portion or a substantial portion is probably having value 0 or any particular value, and for the rest there is continuous distribution or observation. An example is the amount individual spends on alcohol in a given month. So, for people aged above 18 or 21, a significant portion will have no amount spent on alcohol because not everybody consumes alcohol. So, there would be a significant portion of individuals for whom the consumption of alcohol would be 0 or near 0. So, and such preferences are actually not difficult to come across in several other cases. We can find out similar kind of data in many other contexts where the dependent variable takes a particular value for certain individuals, and then for the rest of the individuals we may observe a continuous segment. Alternatively, a very common problem in microeconomic data is censoring of the dependent variable. When the dependent variable is censored, values in a certain range are all transformed to a single value. The approach usually used to estimate models with censored dependent variables is known as Tobit analysis, named after Tobin. Conventional regression methods fail to account for the qualitative difference between limit, that is 0 observations, or it can be some non-zero observations also, and non-limit, that is continuous observations. So, let y be a variable that is essentially continuous over strictly positive values, but it takes on 0 value also with positive probability. Y can be modeled in a linear framework as well, but some of the fitted values can be negative, which would lead to negative predictions for y. So, this is a problem which is similar to the problem that we had encountered with LPM or linear probability model. So, let us assume that y follows a normal distribution and the censoring point is 0. In a censored distribution, only the part of distribution above y equals to 0 is relevant to our computations. So, when data are censored, the distribution that applies to the sample data is a mixture of discrete and continuous distributions. So, basically for those observations for which the dependent variable takes a constant value is the discrete portion, and then for the segment for which the dependent variable takes continuous observations, that is the continuous distribution. Also, the assumption that an explanatory variable appearing in level form has a constant partial effect on expected value of y given x can be misleading. This is also a problem which is similar to the problem we encountered with LPM. Probably variance of y given x would also be heteroscedastic. So, these are various problems because of which linear model cannot be fitted to this kind of a situation, and that is why we need to go for Tobit analysis. Now, because the distribution of y piles up at 0, y clearly cannot have a conditional normal distribution. It has a censored normal distribution. So, all inference would have only asymptotic justification as with the linear probability model. Typically, the Tobit model expresses the observed response y in terms of an underlying latent variable y star. So, what is y star is actually the original variable. So, y star is modeled as y star equals x beta plus u, where u follows a normal distribution conditional upon the values of x, it follows a normal distribution with 0 mean and sigma square as the variance. And the variable that we model is actually y. So, y is equal to maximum of 0 and y star. So, for all positive values of y star, we will fit y equals to y star, and for all values of y equal to or less than 0, this would be 0. So, alternatively we define a new random variable y transformed from the original y star such that y equals to 0 if y star is less than equal to 0 and y equals to y star if y star is greater than 0. The latent variable y star satisfies the classical linear model assumptions that it has a normal homoscedastic distribution with a linear conditional mean. Because y star is normally distributed, y has a continuous distribution over strictly positive values. In particular, the density of y given x is the same as the density of y star given x for positive values, and since we are assuming normal distribution or censored normal distribution specifically for the continuous segment, we are considering a normal distribution. So, that is why for the continuous distribution part, the density of y given x is the same as density of y star given x for positive values, that is when y star is greater than 0, and this density function is equivalent to the density function of the normal distribution, or rather the standard normal distribution, of course, because we are considering y minus xi b beta divided by sigma whole square divided by 2 sigma square. And for y star less than equal to 0, we will be having this as the density function, or rather we probably have here it is equivalent to the CDF or cumulative distribution function of the normal distribution. So, this is our probability response function when y takes the value equals to 0 for given x, that is equal to p y star less than equal to 0 conditional upon x. Now, as we had written y star is equal to x beta plus u, this implies that we also can write x beta plus u less than equal to 0. From here we derive that this is equivalent to the probability that u is less than equal to x beta conditional upon the values of x again. Now, dividing u by sigma, because now we are converting into a standard normal distribution. So, u has a mean equals to 0, but variance sigma square. So, we have u minus 0 divided by sigma, that is equal to minus x beta divided by sigma. Essentially both the sides are divided by sigma, again conditional upon the values of x, and this gives us actually the CDF for minus x beta divided by sigma, which is equal to 1 minus pi x beta divided by sigma. So, from equation 1 and 2, 1 gives us the density function for the continuous range, and equation 2 gives us the response function or density function for the discrete range. From equation 1 and 2, we can obtain the log likelihood function for the censored regression model as logarithm of L, and this is the log likelihood function. You can see that this part corresponds to the continuous segment, that is this segment, and they are summed over yi greater than 0, and this part essentially summed over for the discrete segment, that is this is the segment y minus phi x beta divided by sigma. So, and these are summed over for yi equals 0. This likelihood is a non-standard type because it is a mixture of discrete and continuous distributions. However, in a seminal paper, Amemiya showed that despite the complications, proceeding in the usual fashion to maximize logarithm of L would produce an estimator with all the familiar desirable properties attained by the maximum likelihood estimation methods. So, this essentially implies that despite having a mixture of a discrete and a continuous distribution, maximum likelihood estimation methods are still applicable on this kind of log likelihood functions. Now, we take an example. Suppose that we wanted to model the demand for IPO shares of a company. A as a function of income, age, education and region of residence. So, basically we are trying to find out whether income of an individual, age of an individual, education and region of residence of the same individual would impact the demand for the IPO shares of a company, say A. Now, how we write the equation, but another thing is that the number of shares allocated to each investor is capped at 250. So, investors cannot be allocated shares in excess of 250. Of course, they can place demands which are in excess of 250. But since they will not be allocated shares in numbers more than 250, so what we do is that we basically censor the data. How the data censoring is done? We keep yi equals to yi star for y star less than 250. So, for all those demands which are less than 250, we retain the original value, the actual demand, and yi equals to 250 for all values of yi star which is greater than equal to 250. Now, here we are actually looking at the demand for IPO shares, right, and this is not the actual allocation. So, we are just trying to figure out whether these individual variables or these independent variables, whether they impact the demand for IPO shares or not. Okay, so here yi star represent the true demand for shares and this will be observable only for demand less than 250. For any demand which is greater than or equal to 250, that would be treated as 250. So, unlike the previous example where we had censored the data at point 0, we are here actually censoring it at 250 and 250 is actually on the higher side. So, for any observations lower than 250, we will be actually observing the series. Now, one important limitation of Tobit modeling is that these models are much more seriously affected by non-normality and heteroscedasticity than our standard regression models, and that is why they provide biased and inconsistent estimates. So, possibly the bias and the inconsistency, the biasedness and the inconsistency enlarges when we have a heteroscedastic and non-normal error terms in a Tobit model framework, right. So, this example is just to show you how the data modeling is done or how the framework is actually erected. Of course, estimation methods are complicated and they are produced by standard statistical packages, and the interpretations are very similar to the Probit and Logit model interpretations, because we are ideally specifically Probit model interpretations, because we are specifically applying the same methodology, though it has two segments, one is a discrete segment, another is a continuous segment. Now, we talk about censored versus truncated dependent variables. So, we often would come across also truncated data. Is Tobit analysis applicable to truncated data as well? Censored data occur when the dependent variable has been censored at a certain point, so that the values above or below this point cannot be observed. Even though the dependent variable is censored, the corresponding values of the independent variables are still observable. For example, the IPO shares data is an example of censored independent variable. As you can see that even though the variable value yi was capped at 250, for individual I who has demanded shares equal to 250 or in excess of 250, we would still have observations on his income, age, education and region of residence, right. So, the dependent variable is basically capped or censored at a particular point, but the corresponding independent variables are not at all censored. Their actual figures are still observed with censored data. However, for a truncated dependent variable, the observations for both the dependent and independent variables are missing when the dependent variable is above or below a certain threshold. So, when we truncate data, then we basically sort of exclude those data from the mainframe analysis. Alternatively, we do not have observations either for the dependent or for the independent variables. Thus, the key difference from sensor data is that we cannot observe the excise either, and so some observations are completely cut out or truncated from the sample. For example, suppose that a bank were interested in determining the factors such as age, education, age, occupation and income that affected a customer's decision as to whether to undertake a transaction in a branch or online. Now, suppose also that the bank tried to achieve this by encouraging clients to fill in an online questionnaire when they log on. There would be no data at all for those who opted to transact in person, since they probably would not have even logged on to the bank's website or web based system, and so would not have the opportunity to complete the questionnaire. So, what is happening here is that those who are actually not using online portals altogether, we will not have any information about their age, occupation, income, etc. So, which implies that a segment of the sample is actually not collected altogether, and that is why we say that dealing with truncated data is actually a sample selection problem, because the sample of data that can be observed is not representative of the population of interest. The sample is biased, because as we can see that we were interested to know whether these factors impact a customer's decision to transact in a particular branch or not. But then there are a large number of customers who probably do not use online or internet based interfaces, as a result of which what would happen is that they would be completely excluded from the sample altogether. So, this is a sample biased, or rather a sample selection problem, and that is why this does not represent the true population, or it is not representative of the population of interest. And this is very likely resulting in biased and inconsistent parameter estimates, or possibly we are going for a sample which is probably driven by our convenience. So, of course, the parameter estimates also do not probably reflect the intended measures they are supposed to go for, or they are supposed to produce. So, this is a common problem which will result whenever data for buyers or users only can be observed, while data for non-buyers or non-users cannot. For truncated data, a more general model is employed that contains two equations, one for whether a particular data point will fall into the observed or constrained categories, and another for modeling the resulting variables. So, the second equation is equivalent to the Tobit approach, right. If it is thought that the two sets of factors will be the same, then a single equation can be used and the Tobit approach is sufficient. In many cases, however, the researcher may believe that the variables in the sample selection and estimation equations should be different. In that case, we should be having two different equations. The two equations could be jointly estimated by maximum likelihood. An alternative approach popularized by Heckman is also used for computational ease. However, for the sake of simplicity of the exposition, I have not included the equations and detailed discussions on them, because otherwise they would be too much of time consuming. And other than that also, this is somewhat outside the purview of Tobit analysis, and the computations are also pretty much complicated. Next, we talk about multinomial linear dependent variables. All of the examples that have been considered so far have concerned situations where the dependent variable is modeled as a binary choice, that is 0 or 1 values it has taken. But there are also many instances where the dependent variable has multiple categories. Suppose our dependent variable is individual investors' investment patterns in terms of 4 broad groups of financial instruments, say deposits, insurance, stocks and bonds. Now, individuals are assigned numbers between 1 to 4 depending on how many instruments they have invested in. So, for example, if an individual has invested or holds only deposits like accounts, then he would have a score of 1. Someone who holds money in deposits and stocks and bonds will have a score of 3. Someone having all 4 instruments will have a score of 4, and so on. So, multinomial logit or probit models are used when the categories of the dependent variable do not follow any order. In case they can be ordered, an ordered probit or logit model is used. So, we will be having 2 broad categories, one of multinomial logit or probit models, another is of ordered probit and logit model. Again, due to paucity of space and time constraint, I am going to discuss multinomial logit and probit models broadly, rather multinomial logit to be more specific, and the interpretation or the models with respect to probit are all very similar in terms of interpretations and modeling structure. The way logit and probits are very similar, and also I am not going to discuss an ordered probit or logit model, because first of all there is constraint, and the other thing is that broadly the interpretations and structure and framework would be very similar, right. There would be slight differences in the estimation mechanism, because we would be having ordered logit model. So, we had discussed ordered logit or probit model while dealing with binary choice. So, that can be extended to a multinomial logit or probit model very easily. So, when the alternatives are unordered, this is sometimes also called a discrete choice or multiple choice problem. Econometrically, this is captured using a simple generalization of the binary setup discussed earlier. So, when there are only 2 choices 0 and 1, we require just one equation to capture the probability that one or the other would be chosen. If there are now 3 alternatives, we would need 2 equations. For 4 alternatives, we would need 3 equations, and so on. So, that is how in general, if there are m possible alternative choices, we would need m minus 1 equations. The outcome for which an equation is not estimated becomes the reference choice, and thus the parameter estimates must be interpreted slightly differently. So, in this context, as I have told you that I am going to consider only multinomial logit models for discussion. Note that if f beta prime xi, where f represents the cumulative density function, is defined as this, then a logit transformation of the f function, which is basically which follows a logistic distribution, is given as g x, where logarithm of f beta prime xi divided by 1 minus f beta prime xi is equal to beta prime xi. So, this is a simple mathematical calculations. If you plug in the values of f beta prime xi here and take the logarithm, then you would arrive at beta prime xi. The importance of this transformation is that the logit of the multiple logistic regression model G x has important properties, like it is linear in parameters and can take any value between minus infinity to infinity. So, the advantage with this is called logit function, and logit function is certainly not same as logit model. Logit model is basically based on this logistic regression, or we call it logistic distribution, or we also call it logistic regression, where this logit function is basically equivalent to a linear combinations of the xi's, and the advantage it has is that it can take value anything between minus infinity and plus infinity, which implies that the constraint within which the logit model operates, that is between 0 and 1, probability should be between 0 and 1, is not there with the logit function. Now, assume that the dependent variable has 3 categories coded as 0, 1 and 2, with 0 as the reference or baseline category. One can always choose any category as the baseline category while using any software package, but most often it is common to consider 0 as the reference or baseline category. Further, we assume that there are k plus 1 independent variables, including the constant term denoted by the vector x. So, here we are using this bold x small x, which actually consist of, or which consist of all the independent variables, k plus 1 independent variables for specifically an individual. The 2 logit functions are denoted as g1 x, which is basically logarithm of f x prime beta 1 minus x prime beta 1, that is basically logarithm of the ratio of the response probability of y equals 1 conditional upon x to the response probability of y equals 0 conditional upon x. I am writing all these things just to recollect that all these things were actually done previously while discussing the Logit and Probit model. So, that is why these things have been written here. Otherwise, from the previous slide it straight away follows that g x equals to beta prime x I. So, here the g 1 x is equal to x prime beta 1, which is basically you can see that linear combination of the betas and the x's. Now, the second equation has g 2 x, which is again a linear combination. You can see that beta 2 is a vector, beta 1 is also a vector, and they here beta 1 0, beta 1 1, beta 1 k are the parameters, while here the parameters are beta 2 0, beta 2 1, beta 2 k. So, the parameter estimates are going to be different for in the two different equations. It follows that the conditional probabilities of each outcome category given the covariate vectors are basically probability, this is the response function, probability of y taking a value 0 conditional upon x is given as 1 upon 1 plus e raised to the power g 1 x plus e raised to the power g 2 x. And similarly, I will be having probability response function for y taking the value 1, where we will have e g 1 x in the numerator, and probability y taking the value 2 conditional upon x takes e raised to the power g 2 x in the numerator. The denominator remains same in each case, and since y equals to 0 is the baseline or the reference category, the numerator is 1 here. Now, coming to the interpretation of these models, first I will be introducing the concept of odds ratio. So, useful concept in the interpreting multinomial logit model is the odds ratio or OR. Suppose there is only one independent variable and it takes value x equals to 0 and 1. The odds of the outcomes being present among individuals with x equals 0 and 1 are f0 divided by 1 minus f0 and f1 divided by 1 minus f1 respectively. Now, where f1 and f0 have the usual interpretation, as you remember from here, and we have been defining f like this since the beginning of the discussion on the Logit and Probit model. So, when we are having x is equals to 0, then of course, we do not have the x1 variable, and that is why we have only the intercept, which is e raised to the power beta naught. When we have x is equals to 1, then that function x beta, x prime beta is basically beta naught plus beta 1 x, and x is equals to 1. So, we have e raised to the power beta naught plus beta 1, and again the numerator remains basically here 1 minus 1 plus e raised to the power beta naught plus beta 1, and here 1 plus e raised to the power beta naught. The odds ratio is the odds for x equals to 1 to the odds for x equals to 0, and is given by the ratio of these two, which turns out to be e raised to the power beta 1. So, this also depicts the relationship between the odds ratio and the regression coefficient for a logistic regression model with dichotomous independent variables, variable coded as 0 and 1. So, this is the relationship between odd ratio and the estimated parameters beta 1 or betas. Now, generalizing, suppose the dependent variable has j categories, y equals to j, where j takes the value 0 1 to capital J, where 0 is the base category. Then the odds ratio of y of the outcome y equals j versus outcome y equals to 0 for explanatory variable values of x equals a versus x equals b is basically given as this. So, you can see that probability of y taking the value j conditional upon the value of x equals to a divided by probability of y taking the value 0 again conditional upon the value of x equals to a. And similarly, in the denominator we have the alternative values of x, that is equal to b, and then probability of y taking the value j divided by probability of y taking the value 0. With 3 categories of y, the odds ratios are calculated from the estimates given in the table. So, we are considering here an example where suppose the dependent variable is the travel modes. So, bus is the baseline category, metro and taxi are the 2 categories denoted by 1 and 2. So, we are trying to find out that if we have 2 categories of the independent variable, that is people having income less than average and people having income greater than equal to the average. So, we collect data on individuals' preferred mode of transport and their income level. We find an average of the income of the individuals or of the sample, and then categorize the individuals into 2 groups, having income less than average, having income greater than equal to average. And the odd ratios are calculated following the formula, and they turn out to be 1.79 in the first case and 3.10 in the second case. You just need to plug in these values into this formula, right, and in order to arrive at these odd ratios. The calculations are already being shown here. So, the odds ratio is widely used as a measure of association, as it approximates how much more likely or unlikely it is for the outcome to be present among those subjects with x equals a as compared to those subjects with x equals b. The result would be interpreted as follows: the odds among people with average and or above average income to travel by metro to workplace is 1.79 times greater than the odds among those with below average income. So, this is 1.79 times greater for people having income greater than or equal to in average compared to people having lower than average income. Similarly, the odds among people with average and or above average income to travel by taxi is 3.10 times greater than the odds among people with below average income. So, this is basically the second odd ratios, and this essentially facilitates the comparison that what are the chances or likelihood that the individual having an income above or equal to or above average will travel by taxi, or in this case he will travel by metro. So, that is broadly about the multinomial logit model as well as probit model, and that completes the segment on binary dependent and independent variables. This is the references I have followed in order to come up with the discussion or today's discussion. Thank you.